Hello and welcome back to Let's Code Physics. We are continuing to dive into the world of two-particle wave functions. Last time we got a look at some interesting behavior with the Lennard-Jones potential energy. Just to remind you, this is a potential energy that has an attractive part and a repulsive part. It's attractive when the two particles are far away, so it goes like this negative r to the negative 6 term. When they get close together, it goes like this positive r to the negative 12 term. And it's the location of the minimum between the two, this r min, that seems to be the interesting driver of the behavior. Last time we had r min set equal to 1, and we were getting an average distance between the two particles for their expectation values of about 0.1. So it's about a tenth of that, which is interesting because it's just far enough from 1 that it could be 1, it could not be not 1. Another culprit for determining that length scale could be this amount that we displaced the wave function by initially, this minus 0.2, because 0.1 is half of 0.2. So as my PhD advisor likes to say, this is where you play the numerology game to try to figure out which of these numbers is determining the length scale in the results, because whatever kind of scale you have in the results has to in some way be determined by the natural scale that you input into the problem. And so one way we can investigate this is by looping over the code several times. So instead of having it run just once and producing one set of results, we can have it run several times and produce a family of curves. The way we're going to do that is by looking at both of these variables, by looking at r min and then by looking at this initial displacement. I'm going to start by varying r min. So the goal for today is for me to show you how I'm going to set up this loop over the entire code to change the r min value, and then I'm going to let this run overnight again, and then we'll come back and discuss the family of results, and then I'll make the changes for this piece, for the initial wave function displacement. Loop it overnight again. We'll discuss the results. So you'll see me changing outfits a couple times, I think, as I run this over the course of the next few days. But let's get started with some of the basic things we'll need to do. The first thing I'm going to need to do, in order for this to run within a few days instead of a few weeks, I need to get rid of all of the wave function animation. I think we've kind of gotten all the lessons that we're going to get from the wave function animation itself. So we're going to take out the animation entirely. So anything having to do with the animation, I don't have to worry about anymore. I still have to keep the grid. I still have to keep that mesh in place. I still have to calculate the wave function, obviously. But I don't want to be worried about it updating, that 100 some odd white dots on the screen. So for example, here we've got the create the flat surface for graphing. I don't want to worry about dot list anymore. Let's see, I think I can just comment out this entire thing. It's been very helpful, but I just don't need it anymore. There we go. We can double hash those out as well just to match. There we go. Let's see here, psi previous calculation, I still need that. And basically I just need to remove anything having to do with dot list. And here we go. So I no longer need this loop. So that's going to save me time in terms of looping. It's also saving me a very intensive computer operation because the computer does have to think through some things to actually render the animation. Dot list here, same thing. 3, there we go. So Alt-3 in VPython will automatically take care of commenting something out for you. Alt-4. Not Alt F4, but Alt 4. Don't press Alt F4. That can be bad news. We'll uncomment them or decomment them. Okay, cool. It looks like we've removed the visuals there. The next thing I want to do is I want to change the expectation value calculation. So instead of having it display both of these, right, I'm going to get a family of curves. So what I'm going to have it do is I'm going to have it calculate for me the difference in the expectation values. So let's see here. So this one we're going to get rid of. Why don't we get rid of that? I've saved this under a different file name. So we're going to calculate expectation value of x minus y. Let's see here. So this is going to be, now instead of x, we're going to have x minus y of ix. Cool, there we go. And then I can get rid of this calculation entirely. Cool. Expectation value of x, expectation value y. I don't need two plots anymore. Let's see here. Yeah, that's fine. And again, this is going to be x minus y. Just remind myself I've already changed. I can go and get rid of the momenta calculations. Again, here, this now needs to be x minus y of iy. Did I make that an x? Did I make that a y of ix or y of iy earlier? Oops, I made it a y of ix earlier. I'm glad I thought to check that. Okay, cool. So here, where did I leave off? Okay, I left off down here. I can get rid of these. I can get rid of all of these. I can get rid of that. Let's see here. Okay, cool. Let me just go back over and double check those. Okay. Expectation value of x, good. Ix minus iy, excellent. Let's see here. Ix minus iy, awesome. Awesome, 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 awesome. Okay, cool. So I've taken care of looping over the expectation value calculation. So now what I need to do is I need to have this G curve here reset every time. So this is actually where I need to start the loop. So let's start thinking about some rmin values that I would like. So what I'm going to do is I'm going to create an array called rmin a. For rmin array. So this is going to be the array of rmin values, because I don't necessarily want to go in linear order. I don't necessarily going to go 0.1, 0.2, 0.3, and 0.4. I want to try some different orders of magnitude as well. Let's see, for example, do I want to start with 0? I kind of feel like starting with 0 is going to be a bad idea, because rmin of 0 is going to make this thing 0 entirely. Yeah, so I don't want to do that. Let's start with something small, because one of the things I want to check is you know, which of these length scales is determining the behavior to particles. Is it rmin or is it the initial wave function displacement? So the initial wave function displacement is currently 0.2, and I'm working on a scale of about -1 to 1, right? Because I have to glue down so much of the initial wave function. So let's, which now I don't get to visualize anymore. So let's put this one at, let's go all the way down to 0001. I'll check this and then I'll add more values on later if I need to. And then we'll do rmin a dot, actually I can just set them all here, can't I? So let's see here. So to make a list, I just need to put in some commas. Cool. So then we'll do 0.0. Why don't we do 0005? Let's go in increments of sort of half an order of magnitude, if you will. I know it's not exactly half on a log scale, but humor me. Let's see here. So that's 0.0005, 0.001, 005, 0.01, 0.05. And actually, let's even pick out a special value of what's the initial separation? 0.2, right? Yeah, this is initially 0.2. Excuse me. Yeah. Let's do pick 0.2 when we get there. So 0.1. Actually, here let's start going in linear order now. 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. 0.9. Let's go all the way up to 1.0. I don't really want to go too much higher than that, because then they, you know, the interesting stuff of the potential might exceed the size of my grid. So I've got 0001, 0005, 001, 005, single 01, single 05, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. Cool. That's how you count, right? That's how you count. So then what I need to do is I need to wrap this whole thing in a loop, So what I need to do is have this be for rmin in rmin. See, I did learn how to do a for loop. And now what I need to do is I need to take everything, the entire code, well, maybe not end of program, and I need to indent it to make it underneath that. And that did not work. Why did that not work? Alt indent. I thought, format indent read. Oh, it's control, not alt, excuse me, control indent. There we go. So now I have indented everything. So now everything, save for end of program, but it should really only be printed once, is all in this loop for rmin in rmin. Let's see here. And then what I need to do here is I need to make that a global variable so that way it gets read in. So I'm going to say global rmin, and I want to take out this part here. Actually, we can get rid of this stuff from earlier, can't we? I'm not terribly interested in testing emin. If nothing of interest seems to change, I might change that one. But I'm going to try the rmin. And then basically what I'll do for the next run is I'll have it change the wave function displacement. So WFD is 0.2 currently. So this is the wave function initial displacement. And then I'll go ahead and make that a global in here. Global WFD. We'll make this, instead of 0.2, we'll make it WFD. Global just means that the function knows to bring that value in from outside the function. Because usually when you go into a function, it clears all the variables that you're looking at. Cool. So what I'll do is I'm going to do a couple things off camera so as not to completely bore you, because I want to save time on this video and some of your attention, which I know psychologically has been proven to be a limited quantity in humans. Attention is. I want to run this, and then I'll change it to run, instead of an rmin array, it'll be a WFD array. And so it'll run for WFD in WFDA. And then that way I'll run that. I won't bother showing you changing that over. But another thing I'm going to add in is I'm going to have this write to an external file, because it's entirely possible this will take longer than one night to run, and I need to have this laptop at my 3-hour exam tomorrow morning so that I don't go stir crazy. And so I may need to interrupt it and then come back. So I'm going to look up how to write this data, these data to an external file, and then we'll examine it with Excel or GNU plot or something like that. So I'm looking forward to running this. I will see you on the other side. Hey, it's me again. There are a few other things that I forgot that I would need to do. One thing, very important, I need to put a cap on the amount of time that each individual simulation runs. So I think we were getting out to about 3 seconds or so, or 3.0 time on the last couple. So I just put while time less than 3. That should give us plenty of data points to look at. I was also able to get it to write to an external file pretty easily. This is what it looks like, just to give you an idea. So it records the rmin value, it records the time and the expectation value. And I was looking down this, I said, all right, it means it's going to continue until, and then I realized I hadn't put in a maximum time. So that's important. I also took out the graphing entirely. So I took out all the .plot commands and all of the, and the creating the G-curve, because I realized for writing an external file, I don't need to graph it in real time. Anyway, I'll just graph them all later. So basically what it does is it opens a file with the name rmin and then the value of rmin.txt, and then it basically puts into there the values time and the expectation value. I also had to remember to put in a new line command there, otherwise it's just a string of data. So anyway, this is something that Excel will be able to read. So I'm going to set this up to run, and I'll see you in a little bit. And we are back. So for you, that's been a few seconds. For me, it's been a week, which for you has been the week of no videos. So now we are more or less caught up with each other. What you see here are the results of the looping over rmin. I've got this open as a PNG file because the amount of data that the code was writing out, because of that teeny tiny time step size, is about 6 megabytes per run. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 runs. So that's 13 times 6 equals a lot of megabytes. So I opened it in Excel, managed to get it to create a graph, and then took a screenshot of it before it crashed, which is why I don't have a chart title or axis labels. Sorry. Yes, you're supposed to do that in science, but literally Excel was having trouble handling it. But I do have some extra data compared to what I was going to show you, which is good news. Basically, this is the time axis. The horizontal axis is time, just like it was in our animation before. And then the vertical axis is the expectation value of particle 1 position minus particle 2 position, or 2 minus 1. It doesn't really matter which one because it's just labels. And so this is for a constant initial wave function displacement of 0.2 along the particle 2 axis. And then the different traces, the different curves, are for various values of R min. Again, that's where the minimum in the Lennard-Jones potential occurs. So this is really interesting. What you notice is that for most of the graphs, they look pretty much the same, right? There's a little bit of a change in the location of the peaks and troughs. But when you look through the, let's start at the lower value ones. So this kind of darkish gray here. Actually, is that the one I want to look at? Yeah, that's the one I want to look at. Excuse me. Having to remind myself. So if you start, at kind of the lower values here and then work your way toward the higher values, what you can see is that there's a pretty distinct shift between the yellow one and the that first dark blue one there. Okay, now I've got myself oriented. Excuse me. This one here, this light blue one that you see on the very top, that's the R min equal to 1.0. So that's the largest R min value. Okay, yeah, and the one underneath that is 0.9. Excuse me, I was reading these backwards. So we actually want to start up here on these traces. So where it goes, the yellow and the gray. So yellow, min of 0.1. The gray, min of 0.05. The orange, the min of 0.0, which you can just barely see behind that. And then there's another blue one behind there that you can't really see because it's not making a huge difference to change our minimum anymore. Basically, once our min sort of leaves this order of magnitude in the yellow and gray and dark blue range here, then the change stops being so significant, right? So there's a huge change in behavior between the yellow one and the gray one. Excuse me, not the gray one, the dark blue one that's way in the back here. Basically, once you get to this one, it all kind of follows more or less the same trajectory. There's a little bit of adjustment, but the major change is between the yellow one and the dark blue one. When you look at the values of that, that's between 0.1 and 0.2. That's significant because 0.2 is the value of the initial wave function displacement. So what we see is there's a huge difference made when one of those values becomes significantly larger or smaller than the other one. So for this regime up here, for the yellow and gray, so for the yellow so for 0.1 down to 0.005 and presumably down to any lower or minimum value that you want to pick. The wave function displacement is the dominating feature, right? Because that's the thing that's determining what this behavior looks like. But for an R minimum greater than that, so where the wave function displacement is inside the location of the minimum. So you got the minimum and then the displacement is only this far out. Then we get this family of behavior down here. Now it's a pretty significant shift between the yellow one and the dark blue one, between the R min of 0.1 and the R min of 0.2. Again, the 0.2 is where it's equal to the wave function displacement. So I did another run where I explored the values in between 0.1 and 0.2. This time I was a little bit smarter. I managed to get it to save as a PDF, so it looks a little bit cleaner. I bet we can zoom in on that a little bit. There we go. I was also had the insight, oh wait, I don't need all those data points, meaning that the code doesn't have to run so slowly and Excel doesn't have to crash so easily. And so this has fewer data points. So there's more space in between the data points, but you can still get an idea of what they look like. So this is going from 0.1 to 0.2. So we're starting at 0.11, ending at 0.19. we can see the transitioning happening here. So at the 0.11, again, it's the wave function displacement that is dominating. At 0.12, we get this orange curve, so it's starting to shift downward a little bit. By the time we reach 0.13, it's pretty much following the same trajectory as all the others, the same one that we had down in here. So this actually gives us a better idea of what the transition looks like as we go from our minimum less than the order of the wave function displacement to our minimum greater than the order of the wave function displacement. And of course, you could do the experiment in reverse, right? You could also change the wave function displacement value, keep our minimum constant, and you see a similar shift in the behavior. So this is pretty cool. I am excited about this. I think this is a really good place to end this series. I will probably return to the wave function evolver in a future season, but since it's the end of the spring semester and I've got some new things starting up over the summer, this seems like a good logical place to cap off this series at the end of season 2. Thank you so much for watching. This has been the longest series that I've done, and I know many of you have stuck with it through all the debugging and all the animations and all the sped up animations and all the potential energies. And so this is really this is the tip of the iceberg of the type of study that we could do with this type of thing. So before I sign off, just want to give a couple of announcements. One is you can be looking for an announcement from my Twitter and Facebook accounts about a new podcast that I've started with my brother. Many of you I know watch Kyle Blaine Plays, also here on YouTube. He and I have been kicking around the idea of starting a podcast together, and so we just 2 days ago recorded our first episode of the Square Root of Nerd. Square Root of Nerd is the YouTube channel. The podcast is called the Square Root Podcast because Square Root of Nerd Podcast is just 2 words too long, so it's Square Root Podcast. We talk about stuff that interests us. So the way I like to describe it is if you enjoy the tangents that Kyle and I each go on in our videos, this podcast is sort of the bottle where we keep all those tangents. We talk about things like video games. We talk about scientific discoveries. We talk about entertainment. We talk about movies, TV shows, etc. So if you enjoy our sort of social commentary, then please head on over to the Square Root Nerd YouTube channel. You can also find us on Twitter at Square Root Nerd. Because the of made it too long, so on Twitter it's just at Square Root Nerd. The first episode should be coming up soon. I just sent him my final edits to the show notes for the first episode, so that first episode should be hitting your audio devices soon. The other big announcement is, I mentioned this before, but I'm going to be at the summer meeting of the American Association of Physics Teachers. I'm going to be presenting about Let's Code Physics. My presentation is going to be Monday morning, July 18th in session AC, and 2 incentives for you to come. Well, 3 incentives. So number 1, you get to meet me and lots of other physics educators in person. The other big deal is I will have some giveaways to show off. When those arrive in the mail, I'll be tweeting out a picture of the giveaways to hopefully entice more people to come to the presentation. And also at the presentation, I will be making a very important announcement about the next major project coming to Let's Code Physics. So you have to wait until July 18th to find out. If you come to the AAP team meeting, you can be one of the first ones to find out. So thank you so much for watching. I will see you next time. Bye-bye. Yeah, okay.